Hello, everyone. I'm Haoran, a six-year PhD candidate from Georgia Tech and the supervision Professor Yingyan Celine. Today, I'm very excited to present our recent work on ICML 2024. The title is When Linear Attention Meets Autoregressive Decoding Towards More Effective and Efficient Linearized Large Language Models. This work was in collaboration with Amir from Google DeepMind. The background of this project is that autoregressive large language models achieve state-of-the-art performance, but face two significant bottlenecks. The first one is that attention's quadratic complexity is with the number of token increases. And second is that sequential processing nature of the autoregressive large language model generations, which significantly limits the parallelism during the generation. As shown in this figure, the large language model can only generate one token at each time step, and then generates the next based on all the previous generated tokens. Previously, there are efficient model techniques to solve those problems. For attention's quadratic complexity, people proposed linear attention, which can help to reduce the quadratic complexity of attention from quadratic to be linear. And for the second problem, to increase the parallelism, recent study explored the speculative decoding, which employs smaller draft models for speculative parallel generation. Well, those parallel generated tokens will be further verified using the full and large language models. But there are still questions and challenges associated with those methods. For example, for linear attention, previously, linear attention are mostly designed for encoder-based large language models. So another question is that, can existing linear attention designed for encoder-based large language models be effectively applied to autoregressive decoder-based language models? And also for speculative decoding, whether the linear attention and the speculative decoding can be seamlessly integrated to address both the bottlenecks for large language model. To solve those problems, we propose our contributions are made towards the end goal of efficient and effective linear attention, which is also compatible with the speculative decoding. The first contribution is that we conducted the first comprehensive study to evaluate whether existing linear attentions for encoder-based large language models can be effectively work for autoregressive decoder-based large language models. The answer is no. And that motivates our second contribution to propose the efficient and also effective linearized large language model, which can also be compatible with the speculative decoding. So the first contribution, for the first contribution, we have our finding is based on 7 linear attentions across 3 types of large language models. As shown in the below figures, the 3 types of large language models include encoder-based, decoder-based, and also encoder-decoder-based models, like T5. And in the left figure, we found that the 4 kinds of linear attentions worked very well for encoder-based large language models. However, the accuracy will drop a lot for decoder or encoder-decoder-based large language models. And for other 3 linear attentions, it consistently performed bad on all 3 kinds of large language models. So our finding is that existing encoder-based linear attention are not optimally suited for autoregressive decoder-based large language models. And that motivates our second contribution, how to design the efficient and also effective linearized large language models. We consider the effective local argumentations for linear attentions, and also we adopted the grouped linear attention and designed a masked depth-size curve to argument the linear attention. For group linear attention, we partitioned the input sequences into non-overlapping groups. Within each group, we bypassed the local dependencies, allowing for parallel processing. Also, we employed the parallel local attention within each group to make it more efficient. To further argument the LLMs with linear attention, we consider a masked depth-size curve module on top of the V branch, which is the real activation and needs argumentation to better capture the local information, especially for linear attention which lack those information. And note that we adopted a casual mask on those depth-size conv to prevent information leakage. Otherwise, the convolution will convolute the future tokens into the training process. So even though the loss can quickly converge to zero, that doesn't mean the model learned the capability to predict the next tokens. And in addition, we combine speculative decoding with our augmented linear attention to make them compatible. So specifically, the compatibility issue is that for speculative decoding, it alerts the temporal dependencies, and that is not effectively captured by our masked depth-size convolution and also grouped linear attentions. To this end, we propose the updated design of unfolded depth-size conv kernels and the temporal dependency aware group linear attentions that can take into consideration the temporal dependencies represented in the Mandusha's tree-based attention mask. Here, Mandusha is one representative of the speculative decoding method. So in this way, the speculative decoding and our augmented linear attention with depth-size conv is fully compatible. We conducted comprehensive experiments to validate the effectiveness of our proposed linearized relationship models. We consider three kinds of tasks, including language modeling, text classification, as well as zero-shot downstream tasks, using the following datasets and 5 large language models. For these three tasks, we consider the corresponding state-of-the-art baselines to benchmark, including Flash, local, global, linformer, performer, transnormer, and also quadratic softmax-based attention, which is the original large language models. Our experiments show that as compared to the original large language model with softmax-based attention, our linearized large language models can reduce latency by up to 56% and memory usage by 36%. And also it can help to extend the maximum supported sequence length from 8,000 to 32,000 through efficient fine-tuning. This is particularly important for long context tasks. And also, as compared to other state-of-the-art linear attention baselines, our augmented linear attentions consistently show a better convergence properties. That means our augmentation techniques is universally applicable to the linear attention method. So to summarize, we conducted two contributions in this project. The first one is the comprehensive study to evaluate whether existing linear attention for encoder-based language models can be effectively applied to autoregressive decoder-based language models. And then we proposed the efficient and effective linearized language models that can be fully compatible with the speculative decoding. That's all for this project. Thank you for your listening.